Thank you very much, organizers, for the invitation. So, okay, so this is the title, Iterative Families of Partitions. So my plan was to do some motivation and then go to this notion. Now, the last time I practiced my talk, it was like 40 minutes. I took 40 minutes, but it's a 25-minute talk. But luckily for me, the first half of my talk was already done by Franz earlier today. Actually, just don't even erase his talk, and here are the formulas from Franz. So that's going to be our starting point. The motivation for what I want to do is, okay, let me write it down. Transition formulas between different types of cumulants. In probability, okay? Okay, so then, well, again, that there was a 40-minute introduction to this talk by Franz. I hope you didn't miss that. So we have formulas between moments to different brands of cumulants, classical, Boolean, monotone, and free. And we can also like try to understand direct formulas between, okay, first inverse formulas. So now go from cumulants to moments, which they are also there. And we can also understand formulas between cumulants and cumulants. Okay, and okay, so the motivation of this work or my talk is to understand this, and somehow I would like to say in a systematic way, right? So in this picture, I don't know precisely all the references, or I mean it would take some time, but I didn't even know this one. But okay, so basically the relations between classical, Boolean, and free, I know they were studied in a paper by Franz. And then in this paper with Arizmendi, Hasebe, Elener, Vargas, they study all of this picture, okay? And the point is that the techniques to go and compute each of these arrows so far were like just kind of looking into each of the families or pairs and trying to understand what's going on there. So maybe there is some stuff behind that. And somehow the point of what I'm trying to do is a systematic way to study this, which is not going to be as precise as some of these formulas, but it's going to give you an idea of how you want to deal with this type of questions. Okay, so first, maybe I should point out that we have all these formulas between these, but one way to relate, I mean, the first formulas that we had are that we have the moments. Okay, I will call Mn, which is phi of A to the n here. And we have these moment cumulant formulas to each of these cumulants. Okay. And in my way of view these things, we start with these formulas. They are given, depending on your probability or the convolution, the additive convolution you want to study. You have these moment cumulant formulas. And then to understand how to go from one to another, what you can always do is go to the moments, and then from the moments go to wherever you want to go. Okay? Good. And that's what I want to talk about. And the other thing is that if someone comes with another type of cumulants, which right now I can mention another type, the idea will be the same. If you know how to relate to moments, then from moments you can go everywhere. And you use like the moments as a base somehow. Okay, so let me give a framework. Okay, this is also from Franz's talk. I will use this closure interval operation later, so remember that. But I will erase it now. Oh yeah, and I forgot to mention this work is not published. It's part of my PhD thesis from 3 years ago. And I have been wanting to write a paper, a small paper on this and put it out in archive, but I haven't done it because I'm not so sure how relevant is this or what will be a good application. So I haven't done that. Like there's been 3 years from that. But when I was thinking about what to talk about here and looking especially at the list of attendance, it was like, okay, I should definitely talk about this because I have seen many of these the names I can cite in the attendance. I didn't know the faces of some, but I knew the names. Okay, and well here, so I wanted also to break the record on citing as most people from the room. So here I will need to add some citations. I can skip now that, but there is of course a Roland Spiker appearing, and there is a Lehner, of course, because I'm using his talk basically. So Lehner in the study of here, and also Octavio Arizmendi in this study. And okay, so now I can give you another formula of this type, which is moments, which I will call m of a variable, as partitions of non-crossing n. And I will write it like this: t, okay, yeah, t to the inner of pi of I will call beta pi t, and I will call this a fixed t. Let's say just R for the combinatorial purposes, and this will be like the t Boolean cumulants. Right. Which were studied by Ojejko and Wyszochansky. Let me write on that. Okay, you can also study another convolution. Oh, there is Marek. So there is another convolution, and you can give some Boolean cumulant. That's how I call them. So fix some t. I guess for the convolution to be positive and all of these, you need some. Maybe this has to be positive. But in general, combinatorially, you can define it like this. And my point is that it's again another moment-cumulant formula with the same structure, summing over non-crossing partitions. Okay. And then I get to also mention another person in the audience, so good. So, and okay, so for instance, we can now put these t Boolean cumulants, which will be another box here. Of course, the t can vary, so it's actually like infinitely many boxes. And then, of course, the point is that you can always connect with the moments and go to the other families with this framework. Okay, so let me now go directly to the framework. So the idea is the following. Okay, maybe forget about the classical case for now, because we don't like partitions. We are in a non-crossing partition conference, so let's forget about crossings. All of the others can be written as follows. So you have some family, and you can represent families. These could be moments or cumulants, and you can write them as a sum over partitions in NCN. And you can put here some function on pi, and then beta pi. So the alpha and beta are families of moments, cumulants, or whatever you want. And the f of pi is some function just depending on pi. And maybe the beta pi is related to another one, so beta n. Okay, so maybe clarify here. Beta pi is the product of logs in pi of beta b. Okay, and so the alphas and betas are just families. These are just the moments or cumulants or whatever you want, some sequence that you want to study related, right? And then the formula, the transition between these is the f, okay? So what is f? F is, okay, I will just care right now about a function from non-crossing partitions to the complex numbers. And let me just also add that f of the 1n partition is 1 for all n. Okay, and I will call this NC circle, like the dual. Okay, so functions from the non-crossing set. Okay, and what is NC? NC is all the partitions. Union n equal 1 to infinity, NC n. Or h if you want. We can put like a NH here in the middle. So like both groups are happy with n or h there. Okay, good. So I want to focus on these functions from every single partition in non-crossing partition to some number could be complex. Okay, so every single formula here we can write it like this, except for the partitions. Even we have the interval. Okay, we can put zeros whenever there is a non-interval, and we have a sum over non-crossing partition. Okay, so everything that is contained in here, we can write it like this, and then we just care about this function f. Okay, so now let's say we have another relation, beta n is related with another function, of course, g pi, to some other family gamma. Okay, we have so gamma n are another family of moments, cumulants, or whatever you want. And then the question is, can we write alpha n as a sum of some function of gamma phi directly? Okay, so the intuition says this, of course, is true. And first, what I want to do is actually compute this h. Okay, so what it's doing here, we have one way to go from alpha to beta, and we have a way to go from beta to gamma. There should be a way to go directly from alpha to gamma, right? It's like okay. So you have two paths here. You can put them together to go directly to some other place. Okay, so let me quickly do the computation. It's not so hard. So we know the alpha n is a sum of partitions in NC of function f of pi. And then we have a product over the blocks of pi of, and then here we have to put the beta n of beta over b, but then the betas are in turn a sum over partition of NC b of f sigma. Okay, and sorry, g sigma, thank you. And then we have the gamma sigma here. Okay. And the main point is that when we are doing this product of sums, we can change into a sum of products. So this is the same. Pi And now here we have a sum. So each partition, I mean, I have my partition pi, and in each of the blocks I'm substituting with a partition. I get a smaller partition, sigma less than pi, over, and then this is gonna translate into a gamma sigma. And then we have a product over the blocks of pi, because we have here a product of G sigma. So G restricted to the partition, sigma restricted to the block of pi. Okay, and then what do I mean by this? This is a very simple example. We have two partitions, one bigger than the other in the usual refinement order, the reverse refinement order. Okay? And so this is bigger than this. We have two blocks. We check the first block, how it is partitioned, and we check the other, and we are putting a partition here, right? So you get a smaller partition. Okay, and then this is a restriction. So this is so the first block, you get this restriction. To the other block, you get this other restriction. Okay, good. So good. Okay, what I wanted to say. So here we are almost done. We now change the order of the sums and collect every term, and we get that h of pi. Let me just copy here. H of sigma is a sum over pi larger than sigma, f of pi, product of b in pi of G sigma restricted to B. Okay. So we can define now a convolution over the set of functions like that, where basically we are just doing f star G gives me H. Okay. And then it's defined in this way. And then I have a convolution that allows me to compute the product of two of these transition formulas into a direct transition. Okay, and okay, so then first result, I guess, is so this is a group. The reason I asked for this to be 1, I mean, it could be different from 0, but it's easier if you ask to be 1. And the point is that NC dual with star is a group. Okay? It's not so hard to find the identity, and the inverse is basically doing this Moebius thing. Okay? Good. Questions? Okay, so I will then say, okay, now come back to the classical case and the partitions. Everything I did, you can do it with all partitions without any problem. So you can also do the same thing, and you also get a group. But also, I mean, the non-crossing didn't affect in anything. And also, this NC is like a subgroup of this. And how you can identify as a subgroup is by looking at this subset of functions on all partitions, supported on NC, which is going to be my set of functions such that f of pi is 0 if pi is not in NC. Okay? And you can see that if you look for functions which are 0 outside the non-crossing partitions, and you apply your multiplication as I defined it there with all partitions, you will end up doing this sum over non-crossing partitions. Okay? Good. And then the question that iterative families answer. So I have like 5 more minutes. Okay. Is the following. if S is a subset of partitions, when the subset support over S, which is defined exactly as there, the functions for all partitions such that they are 0 outside of S, is a subgroup. And the answer to that is what I call iterative family of partitions. So let me quickly put the definition. It should be clear why is that. So S is an iterative family if, okay, a subset of partitions is iterative family, if one, just to simplify, 1n is in my family for all n, not a very important condition. Important condition is if I have pi and sigma in the set of partitions, I have pi is smaller than sigma in the usual, refinement, inverse refinement order. And then if pi, okay, let me, if the largest partition, if sigma is in my set and sigma restricted, so pi restricted to B is in my set for all B in sigma, then pi is in S. Okay, so basically whenever I apply this operation, if I have a partition that is in my set, and I have that all of these are in my set, then when I substitute this, the new one is going to be in my subset. Okay. Good. So that's the definition, and that's the most fun part. Okay, the most fun part is to check examples, which I can do in 1 minute. So it's not so hard to check that P is iterative, trivially. One, if I just take the one partitions, is also trivially there. Okay, the next more common, we can all shout the answer for the third most natural thing, non-crossing partitions. It's going to be iterative. If you take non-crossing and substitute non-crossing, it's still non-crossing. Okay, you can also have intervals. Okay, and maybe, in my last minute, I will do this with the intervals. Why I call it iterative? Because let's say that you start with a family of partitions with only 2 blocks. Let's say intervals with 2 blocks. Take all possible blocks. Okay? That is not an iterative family because you can break this block and then you have more than 2 blocks. So it's not iterative. But if you keep doing the process, you say, okay, this is not iterative, but if I split, it should be in my set. If I split again, it should be in my set. So basically, you can start with a big block and say, if I want a family that contains this, I can break here, then I can break these blocks, then I can break these blocks, and so on. And whatever I can obtain by doing this is in my family. And what is going to be, that is going to be precisely the interval, the set of interval partitions. Okay? Good. So, and there are many interesting examples. Okay, let me just put the last one. The M divisible are also in this set. And yeah, thank you for your attention.